So again, the technique of partial fractions to integrate different types of functions, in particular rational functions. They're in the form of a quotient, p of x over, if you have a p of x, a polynomial divided by a product of linear factors, the decomposition we're going to use is a constant a over x plus a, another constant, let's say capital B over x plus b, plus another constant, say capital C over x plus little c. So if you have linear factors in your denominator, we're going to try to separate that fraction into three little fractions. Now think about what the advantage of doing this would be. It would be very difficult to integrate the first function, right? That big messy fraction. Now how would you integrate each one of those three little fractions that we came up with at the end? Integrate the first one, what would you have? Capital A is just a constant times, what is the integral of 1 over x plus a? If you were to integrate the first one, what would you get? A is just a constant, you would have a times ln of x plus a, right? Because you're integrating 1 over x plus a dx. And how about the second one? It's going to be this b times ln x plus b, the other one c times ln x plus c. So it's much easier to integrate each and every one of these fractions. So our job will be in this section to come up with these three fractions that represent a given, usually complicated looking original fraction. Okay, if your denominator is like the second case I have here, a p of x, a polynomial divided by x squared plus a times x squared plus b, then we're going to be using a different type of partial fraction decomposition, and it's going to look like this: ax plus d divided by the second one plus cx plus d divided by the second fraction, second factor, x squared plus b. Now, how would that help us? Could you integrate the fractions that are given on the right-hand side? Let's think about it. Okay? You could split each one of those into two separate fractions, right? Like ax over x squared plus a. That was a use substitution question. And then b, or a constant, over x squared plus a. That's an arctangent, right? So we can handle those if we can break down into pieces like this. So the thing we should learn from these two examples is, for the first one, if you have a product of linear factors, our goal will be to try to separate them into just a number over the linear factor, another number over the other linear factor. If you have what we call irreducible quadratic, because x squared plus b, can you factor that again into further factors? Think of it as x squared plus 4. Could you factor this any further? X squared plus 4. How can we factor that? X squared minus 4 we can factor, right? What is x squared minus 4? Exactly, that's x minus 2 times x plus 2. So basically, in order for this technique to work, the first thing you're going to do is you're going to factor out the entire denominator as far as you can. And there's a theorem, the fundamental theorem of algebra says you're going to be able to factor everything into either linear factors or irreducible quadratics. Once you're at that point, you'll be ready to apply the partial fractions technique. And one more word of caution, and that is this method only works when degree of the top is smaller than degree of the bottom. So degree of p of x must be smaller than degree of the bottom. If it is not, if the degrees are equal or the top has a higher degree, guess what we have to do first? Long division first, and then you would apply the technique of partial fractions. So this method, as it's given, only applies when degree of the bottom is higher than the top, or degree of the top, in other words, is smaller than the bottom. Now, you could also have all sorts of variations of this. For example, you could have a polynomial p of x divided by, let's say, x plus lowercase letter a multiplied by x squared plus c. How would you separate this into its partial fractions? Now we have a combination of a linear factor and an irreducible quadratic. So use a combination of the two techniques discussed so far. So to separate this, what should my first fraction look like? a capital A, let's say call it a constant A, divided by x plus A plus the second one, bx plus c over the second irreducible denominator. Again, I'm using capital letters to represent the constants on the top, so that they're not necessarily going to be the same numbers as you see on the bottom. Now, the final variation you need to see is something like this. Say you have p of x divided by x minus or x plus, doesn't matter, a linear factor to a power, say to the third power. We call this a repeated linear factor. A repeated linear factor. You have x plus a times x plus a times x plus a. Okay. This we're going to separate into three different fractions. Okay. The first one is going to be a constant, say capital A, divided by x plus a, plus another constant divided by x plus a quantity square. Yes, yet another constant divided by, any guesses? X plus a to the third. In other words, if you have a repeated factor, if the highest power of that factor is 3, you're going to need 3 fractions to split that. If that had been a 5, you're going to need 5 fractions, etc. And what is the situation with irreducible quadratics to a power? So for example, say you have p of x over an irreducible quadratic, something like x squared plus a, let's say to the second power, to make it a little bit easier. This is also a repeated factor because it's x squared plus a times x squared plus a. For repeated factors, look at the power, whatever the power it is, you're going to need that many fractions. Start with the power of 1, work your way to the highest power there. So what will my first fraction look like? First of all, it's an irreducible quadratic, x squared plus a. So the top should be the linear tops, right? Not just a constant. So what would the first one look like? Ax plus b divided by x squared plus a to the first power, or itself, plus cx plus d, because again, we're dealing with an irreducible quadratic. You will always have numerators of this type. To which power on the bottom? To the second power. Again, if you had the fifth power on the bottom, you're going to need 5 different fractions to decompose it. And I want you for a moment to think backwards, okay? If you had these 2 fractions, how would you combine them into a single fraction? That's what you did all along in algebra, right? You had many fractions, you combined them, you got common denominators, right? What would you multiply? Again, we're talking about the last line here. The top and the bottom of the first fraction, what would you multiply that with to get a common denominator? X squared plus a, right? And the second fraction, top and the bottom, by just 1, right? That will give you one single fraction with just that denominator. Think back into each one of these that we have created. Can you get that fraction on the left if you were to get common denominators? Like here, you have 3 fractions, x plus a squared, x plus a to the third. In that case, if you were to add these up, what would you multiply the top and the bottom of the first one? X plus a squared. The second one, x plus a. The third one, nothing. You combine them, you have one single fraction with a common denominator of x plus a cubed, right? So again, thinking backwards, this makes a little bit more sense as to why we're separating it the way we have it on the board right now. Yes?
In that one illustration there, you just said the bottom. Why the b lowercase? Is that not a constant?
It's just a constant. Any letter that I didn't use on the bottom can be referred to as a constant, but let me just be consistent and put ax plus b. It basically just represents a constant.
Okay.
Okay, now we're going to do some examples. Again, we're integrating fractional expressions today by the method of partial fractions. As an example, let's integrate x plus 2 divided by x squared plus 4x plus 3 dx. You know, I think I'm going to make a slight change on this question. Let's make the top x plus 3. X plus 3. The reason I made the change is because I want to give you a question that cannot be done with u substitution, but if I had kept x plus 2, you can actually do that question with u sub. Okay, when you look at a problem like this, let's think back with all the methods we've discussed so far. Always apply the easiest weapon in your arsenal. You know, you don't have to draw this big guns to the, like trick substitution. If you don't need it, if you can do something with u sub, by all means do it by u sub. If there's a simple formula like arctangent formula, you don't need anything fancy. In this case, can we do u substitution? Let u be x squared plus 4x plus 3. What is du? 2x plus 4, and the top x plus 3, we're not going to be able to replace it with just a du or a multiple of du. So we're going to try something different. Now, could I use trig substitution here? Trig substitution usually applies to perfect square sums or differences. We don't have that perfect square here yet, right? So now let's think about this new technique we're discussing. First step, degree of the top is smaller than the bottom. Check, we have that. Second step, go ahead and factor at the bottom. In this case, we have x plus 3 times x plus 1, right? And now we're going to say that this given fraction can be written as the sum of two partial fractions. And what are those partial fractions going to look like? A constant a divided by x plus 3, right? Plus a constant b divided by x plus 1. Yeah. Our job is to find the a and the b, because once we have a and b, see how easy this question is going to be. Integrate two very simple functions, basically. Okay, to find a and b, we're going to get common denominators on the right-hand side. So you can say that a times x plus 1 plus b times x plus 3 over the common denominator of x plus 3 times x plus 1 must equal the left-hand side, right? And this is the only time I'm writing this long like that, because from now on, I will only write the tops, because you see the bottoms, once you get common denominators, the bottoms are going to be the same. So you can multiply both sides with those bottoms. They cancel out. You only have to worry about the numerator. So from now on, that's the only thing I'm going to be writing. So I'll just write down, say that x plus 3 is equal to a times x plus 1 plus b times x plus 3. Okay. Our job is to find a and b. Here's the easiest way to find a and b. To let a be equal to different values. I'll give you the first one. Let x be equal to, you know what, I just changed that question from x plus 2 to x plus 3, but that's going to create a problem because now the x plus 3's can be canceled. Let's make it x plus 5, please. Sorry about the trouble. So please make it x plus 5. X plus 5. The one on the left-hand side, the top of that fraction, we're making it x plus 5. So basically, the given question has changed slightly. And I'm going into all this trouble because I want to give you an example that cannot be done with u sub. So everything on the left-hand side, we're making it x plus 5. Okay. Our job is to find a and b. Here's a little trick. You make x to be something so that the first part would disappear, would become 0. What should we select x to be so that this whole thing becomes 0? X equals negative 1. So let x be equal to negative 1. And here's what we get. Plug in negative 1 everywhere. So you get negative 1 plus 5, which is 4. A times negative 1 plus 1 is 0, so that disappears. Plus b times negative 1 plus 3. So let's simplify this. Negative 1 plus 5 is 4. 0 plus b times 2. From here, what do we get for b? 2. That's the first find. And to find the other constant, you tell me, what shall I let x be equal to? In this equation, you want this time the b term to disappear. So what would make that disappear? Negative 3. So plug into that equation, again, this equation. Let x be equal to negative 3 in that equation. So now you have negative 3 plus 5 is equal to a times negative 3 plus 1 plus b times 0. Let's simplify that. 5 minus 3 is 2. Negative 3 plus 1 is negative 2. So what does that tell you about a? A is equal to negative 1, right? Now let's go back to the original problem. The problem was integrating a over x plus 3, and a is negative 1, plus b over x plus 1, and b is 2, plus b over x plus 1. So once you find the a and the b, the rest is really very simple. We've done much more difficult integrals than these, each individual one. And what will be answer B? For the first one, it will be negative ln of x plus 3. And for the second one, 2 times ln of x plus 1 plus c. Now, what if you had on the bottom something like 2x plus 1? How do you integrate that if you have like 2 over 2x plus 1? You could do a quick u substitution there, let u be 2x plus 1, and ultimately you'll have an extra factor of 1/2. So just don't forget that, because some of the examples you'll see in the book, they don't have just x plus a number, but they may have 2x plus a number. You have to have extra caution when you integrate that one. Okay, let's go ahead and integrate this next example. Everybody got that one? Okay. If you integrate the sum with limits from 2 to 3 of 1 over x squared minus 1 dx. Okay, let me give you a few moments to do this one, then we'll discuss together. We have to factor this one because it's not an irreducible quadratic. It can be further factored as x minus 1 times x plus 1. What if you had something like x squared minus 2? Can that be factored further? Technically it can be, right? X minus root 2 times x plus root 2. Even that one can be factored further. The ones that cannot be factored at all is something like this, x squared plus 2, because then there's no real number. You'll have to go into the complex numbers to try to factor. It's like x plus root 2i minus root 2i, so we don't get into that. But plus sum of two squares is prime. It cannot be factored. Difference of squares we can factor. So again, get common denominators. And only we're going to set the numerators equal because the bottoms are the same anyway. The numerator from the left equal to the numerator from the right once you get common denominators. Then you said let x be equal to, start with 1 if you like. Either one is okay. On the left-hand side, there's nothing to plug. There's no x. That's a constant of 1. On the right-hand side, we have a times 1 plus 1 or 2 plus 0. So what is a? One-half. Then let x be equal to negative 1. Again, the left-hand side is just a constant. On the right now, we're going to lose the a term. Plus b times negative 1 minus 1, that's negative 2. So from here, what am I getting for b? Negative a half. So the given integral becomes a over x minus 1 plus b over x plus 1 and those constants, they can be factored outside one at a time. Questions? Yes. No, because ultimately our final answer will be the same anyway. So now integrating the first one, we have a half times integral of 1 over x minus 1 dx. That's ln x minus 1, right? And then minus a half ln of x plus 1 in absolute values for the second integral. Now, I'm not going to put a plus c because now we actually had limits of integration. And the limits were from 2 to 3, I believe, from 2 to 3. Now, before I plug the limits in there, I'm going to simplify this a little bit. This can be written as 1/2 times ln of, who can tell me the answer as a single logarithm? Exactly, x minus 1 over x plus 1, because this is like ln a minus ln b, once you factor the 1/2 out, and that's equal to ln of a over b, right? So this is going to be ln of x minus 1 over x plus 1. You didn't absolutely have to do this step, but you will see a lot of the problems will break it down like that. And then substitute the limits from 2 to 3. Okay, I will leave the 1/2 there out on the outside of everything. First, plug the limit of 3 in there, so you have ln of, and everything is positive when I plug the 3, so I can drop the absolute values. So I'm getting 2/4. Minus, plug the limit of 2 on the bottom into everywhere you see an x, and we get ln of 1/3. You know, we could use a calculator at this point to get a decimal, but once again, I want to leave the answer in the simplified possible logarithmic form. You have ln a minus ln b once again. How could you simplify that? If you have ln a minus ln b, what is that once again? Ln of a over b, right? So I could simplify it as ln of 2/4 divided by 1/3, which is the same as 2/4 times 3 over 1. That's ln of 6/4 or 3/2. Again, you didn't have to simplify it exactly the way I did it. You could have gotten a decimal at the previous step if you wanted to, but this gives us a chance to practice with the properties of logs a little bit more. You know, the more we practice, I think the better these rules sink in. So at every opportunity I get, I try to use them to simplify the given expressions. Okay, this was yet another example on distinct linear factors. Any questions about this example before we do something a little bit different? So the first two examples were examples on distinct linear factors. Now we're going to do an example on a repeated linear factor, and we're going to integrate (3x divided by x squared minus 6x plus 9. Again, let's ask ourselves, and I can read this question with an easier method. Is there like a package formula for this? Could I use U substitution? Again, these initial checks yield nowhere. If you did not have an x on the top, what could you have done with this if you did not have an x on the top? You could have done a complete to a perfect square and use arctangent perhaps. But in this case, it looks like a perfect example of partial fractions. Let's see if we can factor the bottom. So if we can factor the denominator, what will we get? X minus 3 times x minus 2, right? In other words, In other words, x minus 3 squared. This is a repeated linear factor. You cannot treat it the same way you treat distinct linear factors. What was the rule, or what kind of fractions do we want to have on the right-hand side for repeated linear factors? Something like a constant over x minus 3, and then another constant divided by what? X minus 3 squared. Let's go back to our notes from earlier. This would be like case number 1, 2, 3, 4. Like when we had x plus a to the third power down here. It's a linear fraction, a linear factor to a multiple power. Then you have to split them starting with the power of 1, keep increasing the powers by 1 until you reach the given power. Remember that? For repeated factors, this is what we do. This is how we try to separate them into fractions. Okay, going back to where we were. Here we are. Okay. Once again, our job is to find a and b. Once we find those, we'll be done, because these integrals in themselves on the right-hand side are going to be pretty simple. How can I get common denominators here? The first top and bottom needs to be multiplied by what? A times. What will be the least common denominator? The least common denominator of x minus 3 and x minus 3 squared is what? X minus 3 squared. So we will try to get both fractions to have the same denominator of x minus 3 squared. If that's the case, the first top and bottom is being multiplied by what? By x minus 3. And the second top and bottom? By anything? Just 1, right? It already has at least common denominator. And now that it has the LCD on the bottom and the left-hand side has the same LCD, I don't even have to bother writing them down. They're going to cancel anyway because I have an equality. So what should I write on the left-hand side here? 3x. That's the numerator of the left-hand side. And this is the numerator of the right-hand side once you get the common denominators. Okay, once again, we're in the position of finding a and b. Let x be equal to, how about 3? Okay. So now 3 times 3 is 9 on the left-hand side. The a term disappears. You're just left with b. There is no other term, like if you let x be equal to plus 3 or minus 3 in this case, you're not going to get rid of another term. So when that is the case, pick any other value that you like. Usually simple values are selected, like x equals 0 or x equals 1, something simple that is easy to plug in. How about the value of 0? That seems like a very simple value. So let x be equal to 0 and plug it once again to this equation on the top. So 3 times 0 is 0. On the right-hand side, a times 0 minus 3 is negative 3 plus b. It didn't give us right away a, but luckily we already know b, right? So we can get a out of this. Go ahead and plug in 9 for b. We already got that above right here. So since b is 9, I'm going to put a on this side. 3a is equal to 9. So what does that tell you about a? Okay, I'm substituting x equals 0 into this equation, right? X equals 0. So I got my left-hand side to be 0. And on the right-hand side, I'm plugging 0 for x, so I got negative 3a. And plus b was already there, so I also put that in here, plus b. And now, basically, since b, right, 3a is equal to b, so a is equal to 3. A is equal to 9, a is 3. Okay, let me show you one other way. Maybe it'll make more sense to you. Hold on 1 second. Let's do it one other way, okay? So on this side, we have a 3x. Okay, let's just do it one more time. So you could also do this way. We're going back to this equation once again. x is 0, right? So you have 0 is equal to a times 0 minus 3. That's negative 3a plus b. Keeping everything exactly as they are, not moving them, you have negative 3a plus b, but we got b to be 9, right? So you can also do it this way. I happen to move this 3a, negative 3 on the other side. You can move the 9 if you like. It doesn't matter. Ultimately, it should still give you the same answer of 3. Okay, either way we do it, we get the same answer. Okay, we have the a, we have the b. Can we finish the question? Let's take a look. So we want a over x minus 3. And a is 3 in this case. So 3 over x minus 3. And then looking back to our equation on the top, b over x minus 3 squared. And b was 9. So b over x minus 3 squared. Okay. How can we integrate this? I'll give you a moment to try it. You're going to have to use something different for the first and something different for the second one, but each one should not be that complicated in itself. So let me give you a moment to integrate. The first one is really easy, right? 3 over x minus 3. What is the integral of that? 3 ln absolute value of x minus 3. The other one, it's not going to be an ln function, but you can use a quick u substitution there. If you let u be equal to x minus 3, du equals dx, and you're going to have something like this, 9 times the integral of 1 over u squared du, which is what? What is the integral of 1 over u squared? Negative 1 over u, right? So this is going to be minus 9 over u, and since u is equal to x minus 3, we can leave it like this. Okay, so far we have done distinct linear factors. We've done a repeated linear factor. Now we're going to do something that involves an irreducible quadratic, and those get a little bit more tedious. The example we'll take a look at is the integral of, excuse me, I was in the line mode there. Let me get rid of that. For the last question? Okay. Any other questions about that answer before we try the new one? Any questions? Okay, we're trying one that has an irreducible quadratic in the denominator, and here it goes. The integral of 2x squared minus x plus 4 all over x cubed plus 4x. That should be my first step. I think it's always a good idea to check that degree of the top is smaller than degree of the bottom. Otherwise, remember, we have to do long division as our first step. Again, we have that standard format. Top has a smaller degree than the bottom, so we're good with that. What is the next thing you should try? Factor the bottom completely, as far as you can factor. In this case, there isn't that much that we can do, right? The only thing we can do is take out an x. So now what we have is a linear factor, which is x, or you can look at it as x minus 0. That's your linear factor. And an irreducible quadratic, right? X squared plus 4. Again, we've already talked about this. This can no longer be factored. That is our irreducible quadratic. Let's write two fractions to decompose this integral. What will it look like? A over x. Remember, x is your linear factor. You can look at it as like x minus 0, so it's in the same format as a linear factor. And the other one, bx plus c. Again, we had to use a linear numerator when the bottom is an irreducible quadratic. So now our job is to find the a, b, and c. Let's begin by getting common denominators. The first top and bottom must be multiplied by what? X squared plus 4. And the second top and bottom has to be multiplied by what? This x. So I'm not writing the bottom, but the bottom would be the product of x times x squared plus 4. That is the same bottom on the left-hand side, so I'm just going to let the numerators of both sides equal to each other. And the numerator of the left-hand side is 2x squared minus x plus 4. Okay. Here's the problem. There is no easy number to plug in, right? Like in the last case, if you plug in x equals 1, something just disappeared and made it easier to continue on. Here, there are no linear factors. One thing, though, you can plug in is x equals 0, right? That will be perhaps one way to get some of the answers. But I want to show you another technique here. When you're dealing with irreducible quadratics, yes, you could plug x equals 0, and you're going to perhaps get an equation out of that, or maybe one of your unknowns. But the following actually works better when you have irreducible quadratics. Distribute your right-hand side completely. So you have ax squared plus 4a plus bx squared plus cx equals the left-hand side. And go ahead and get your x squares together. So that's a plus b quantity times x squared. Get all your x terms together. There's only one x term. Get all your constants together. Only one constant, 4a. You see what I did here? I combined them under the x squared term, the x term, and the constant term. Now rewrite the left-hand side, which was 2x squared minus x plus 4. What I'm going to do is I'm going to use the following logic, which says, okay, if I have an x squared term on the left and an x squared term on the right, their coefficients must be equal. Like, what is the coefficient of x squared on the left? 2. The coefficient of x squared on the right, a plus b. So that gives me a simple equation. A plus b must be equal to 2. Now look at your x terms. Over here, the coefficient is -1. Over here, the coefficient is c. So c has to be -1. And look at your constant terms, 4a on the right-hand side and 4 on the left. So these three equations are going to help us solve for a, b, and c. So let's do that. So first of all, I'm going to do the easy ones first. So the constant has to be equal to the constant term here. So 4 must be equal to 4a. That's one equation. Then I'm going to set the other ones equal. The -1 must be equal to the coefficient of x here. And the last one is going to be the coefficient of x squared must be equal to the coefficient of x squared on this side. So let me write those equations down real quick. Okay, so a plus b must be equal to 2. -1 must be equal to c. And 4a must be equal to 4. So we already know what c is. We also know what a is, right? With that, can you tell me what b is? We know what a is now, right? Put the a back in there, and what do we get? What is b? 1, because we plugged 1 for a, so b is 1. Okay, let me stop for a moment, see if there are any questions about how we got the a, b, c in this case. So usually when you have irreducible quadratics, it's usually easier to multiply it all out and then set the coefficients of equal or like terms equal to each other. Please know that you can use a combination of things. Like for another question, if you get very long equations here, like a plus b plus c is equal to 7, and like 3 equations with 3 unknowns, and you don't want to remember your matrices or something like that, in that case you can use combinations, like let x be 0, let x be 1, and maybe when you do this you get c equals something. So you don't be stuck with just one method or the other. You can combine them to solve for the unknowns. In this case, let's put everything back together. On the top, we had a over x. So our original integral was a over x, which is basically 1 over x. And then bx plus c, that's 1 bx plus c, divided by x squared plus 4 on the bottom. So this is what we need to integrate now. And I need your suggestions. For the first one, the integral of 1 over x, ln of the absolute value of x, correct? And the second one, you can split into 2 further fractions. Basically, you could integrate x over x squared plus 4, and then minus 1 over x squared plus 4. Okay, what is the second integral going to be? You need to do a quick u sub there, right? Let u be x squared plus 4, du is 2x dx. So what will the answer be? Exactly. If you go through your u substitution, you're going to get 1/2 ln u, which in this case is x squared plus 4. And the last one, tangent inverse, right? The last one is direct application of the tangent inverse formula. So what should I be writing here? 1 over a, which is 1/2, tan inverse of x over a, which is just enough room to put my plus c. Okay, so this was an example that had an irreducible quadratic in it, and we have to remember to change our numerator accordingly. And I'll answer any questions you may have on this in just a moment.